Have you ever looked up at a plane cruising thousands of feet above you and wondered what it's actually flying through? We tend to think of the sky as just empty space, but it's not. It's an ocean. Welcome to our deep dive into weather theory and aviation hazards. Today, we're starting with the absolute basics, the Earth's atmosphere. You can think of the atmosphere as a massive cloud of gas and suspended solids. It extends from the surface where you're sitting right now, out into space, for many, thousands of miles. The higher you go, the thinner it gets, but it's always held tightly in place by the Earth's gravitational pull. In short, the atmosphere is the protective bubble that people, and pilots, live and work in. It holds the air we breathe, shields us from the harsh radiation of outer space, and acts as a massive reservoir for moisture, gases, and tiny particles. Virtually everything we do is affected by the weather, which is simply the state of this atmosphere at any given time and place. But of all human endeavors, absolutely nothing is as deeply connected to the weather as aviation. Understanding this invisible ocean is the very first step to becoming a safe and knowledgeable pilot. So, let's unpack the composition and the vertical structure of the sky. If you could take a scoop of the sky and analyze it, what would you find? The Earth's atmosphere is a highly specific cocktail of gases. Nitrogen, oxygen, argon, and carbon dioxide make up 99.9998% of it. Nitrogen is the heavy hitter here. It's by far the most common gas, and it serves a critical purpose. It actually dilutes the oxygen. Without nitrogen, the oxygen concentration would be so high that fires would burn rapidly and uncontrollably at the Earth's surface. Plus, living things need nitrogen to build proteins. Then of course there's oxygen, essential for the respiration of all living things. We also have carbon dioxide, which plants use to create more oxygen. But carbon dioxide has a second job. It acts like a giant thermal blanket, preventing the heat from the sun from escaping back into outer space. Now before we start climbing in altitude, we need to introduce a concept that meteorologists and pilots use all the time: the air parcel. Imagine a small, invisible cubic centimeter of air, sort of like an invisible balloon. This is an air parcel. It's an imaginary volume of air that is large enough to contain millions of molecules, but small enough that its temperature, pressure, and humidity are completely uniform inside. Throughout your aviation journey, you'll hear about how air parcels rise, cool, sink, and expand. It's the ultimate tool for understanding how weather is born. All right. Let's start our climb. The Earth's atmosphere is divided into 5 distinct concentric layers. These layers aren't separated by brick walls, but by changes in temperature, chemical makeup, and density. Layer number 1 is the troposphere. This begins right at the Earth's surface and extends up to about 11 kilometers, or 36,000 feet. This is our home. This is where we live, breathe, and where almost all of the Earth's weather occurs. In the troposphere, as you climb higher, the gases decrease and the air gets thinner. Because the air is thinner and further from the heat radiated by the Earth's surface, the temperature drops fast. If you take off on a pleasant 15 degrees Celsius day, that's 59 degrees Fahrenheit. By the time you reach the top of the troposphere, the temperature will have plummeted to a bitter negative 56.5 degrees Celsius. But the troposphere isn't a perfect sphere. Its depth actually changes depending on where you are and what season it is. At the equator, the troposphere bulges out to about 11 to 12 miles high. But if you fly to the North or South Pole, it shrinks down to just 3.7 miles high. Down at the very bottom of the troposphere is what we call the planetary boundary layer. This is the air physically scraping against the terrain, buildings, and trees. Its height changes depending on the time of day and how much the sun is heating the ground. This boundary layer is the engine that transports heat and moisture up into the sky. When you reach the ceiling of the troposphere, you hit a transition zone called the tropopause. Everything below this line is considered the lower atmosphere. Pushing past the tropopause, we enter the stratosphere. This layer extends up to about 50 kilometers or 31 miles above the Earth. The stratosphere contains about 19% of all atmospheric gases, but almost zero water vapor. And here is where things get weird. The temperature actually increases as you climb. Why? Because the stratosphere is home to the ozone layer. As oxygen molecules absorb intense ultraviolet radiation from the sun, they form ozone. This absorption generates heat, so the temperature rises from that freezing negative 56 degrees at the bottom up to a relatively balmy negative 3 degrees Celsius at the top. Because the temperature is rising with altitude, the air here is very stable. It doesn't want to mix or churn. That makes the stratosphere incredibly calm. This is exactly why commercial airliners climb up into the lower stratosphere to cruise. They are literally flying above the weather to avoid the turbulence and convection happening down in the troposphere. However, it's not always a smooth ride. Sometimes, violent thunderstorms in the troposphere are so powerful that their tops punch right through the tropopause and overshoot into the stratosphere, causing severe turbulence for those airliners. There are other trade-offs to flying this high too. The warmer temperatures compared to the tropopause can actually decrease engine efficiency, increasing fuel consumption. Plus, crews and passengers are exposed to higher levels of cosmic radiation and increased ozone concentrations. Leaving the stratopause, we enter the mesosphere, extending up to about 53 miles high. Here, the air becomes unimaginably thin. Because we are above the ozone layer, we lose that warming effect from the UV radiation. So, the temperature starts dropping again, plummeting to as low as -100 degrees Celsius, or -148 Fahrenheit. But even though the air is incredibly thin, there's still enough of it to protect us. When space debris and meteorites hurtle toward Earth at thousands of miles per hour, the friction of hitting the sparse gases in the mesosphere causes them to burn up. When you see a fiery shooting star in the night sky, you are watching the mesosphere doing its job. Next up is the thermosphere, stretching all the way to 430 miles above the Earth. This is the realm of the upper atmosphere. Here, the gases are so sparse that only the highest energy UV and X-ray radiation from the sun is absorbed. But that tiny bit of absorption causes the temperature to absolutely skyrocket, reaching up to 2,000 degrees Celsius, or 3,600 degrees Fahrenheit. But here is a fascinating physics paradox. If you were to stick your arm out the window in the thermosphere, it would feel freezing cold. Why? Because temperature is just a measurement of how fast molecules are moving. The few molecules that are up there are moving incredibly fast, but there are so few of them that they wouldn't be able to transfer enough heat energy to warm your skin. Finally, we reach the outermost layer, the exosphere. Extending from the top of the thermosphere out to 6,200 miles, this is the fading edge of our planet. Atoms and molecules are so far apart here that they regularly just drift away and escape into the void of space. This is where many of our satellites orbit, so we've traveled from the surface all the way to space. You've seen how temperature, pressure, and density fluctuate wildly depending on how high you are, what latitude you're at, and what season it is. And that creates a massive headache for aviation engineers and meteorologists. How do you design an aircraft or calibrate a sensitive flight instrument like a pressure altimeter when the atmosphere is constantly changing? You have to invent a baseline, and that is called the standard atmosphere. By international agreement, scientists created a hypothetical fixed standard. It represents the average atmospheric conditions across all latitudes, seasons, and altitudes. In the standard atmosphere, at sea level, the temperature is exactly 15 degrees Celsius, and the pressure is exactly 29.92 inches of mercury. From aircraft performance calculations and missile design to the way your instruments read your altitude, everything is referenced back to this standardized model. Whenever you read a flight manual or a meteorology handbook, unless it says otherwise, it is assuming you are flying in the standard atmosphere. The atmosphere isn't just empty space, it's a dynamic, layered, and complex fluid that dictates how, when, and where we can safely fly. From the life-giving boundary layer of the troposphere to the smooth but heavily irradiated cruising altitudes of the stratosphere, understanding these layers is what separates a good pilot from a great one. Next time you look up, remember, you're looking at an ocean. Thanks for joining us for this dive into weather theory. If you found this breakdown helpful, make sure to like, subscribe, and hit the notification bell so you don't miss our next lesson on aviation hazards, where we'll look at what happens when this atmosphere fights back. Fly safe, and we'll see you in the next one.